I'm excited now to introduce our next speaker. He is our keynote, and he is truly one of the visionaries that have made possible autonomous and electric aviation. So we are definitely honored to welcome our next guest. Dr. John S. Langford is an aerospace entrepreneur. He created the Daedalus Project in 1985, founded Aurora Flight Sciences in 1989, and founded Athena Technologies in 1998. He is currently the founder and CEO of Electra.aero, a startup developing hybrid electric regional aircraft. He is a member of the National Academy of Engineering and serves as the current president of the American Institute of Aeronautics and Astronautics, the AIAA. So it is my great privilege and pleasure to welcome to the stage Dr. John Langford.
Well, thank you, George, and it's a great honor to be here. I wanted to thank Jim for setting this up and inviting me. And although I've never formally studied at Ohio State, I do consider it had to have been a really important part of my education, primarily through the work of Dr. Gerald Gregorick, who many of you probably know through his long service in the Department of Aeronautics, as well as to the American Institute of Aeronautics and Astronautics. And you know, we lost Dr. G last year, but his contributions live on, and I wanted to start this with a salute to him and the work that he'd done. I'm also really pleased to have a number of the students here today, and particularly from the AIAA section and chapter. That's a huge part of our profession, and welcome especially to the students, and encourage everybody to be a member of the professional operation. And then the last thing before I start is just to say that the comments I'm making here today are really just me speaking as an individual. They don't represent either the AIAA or Boeing, where I just left about a month ago as part of Aurora. But I do want to try to pull together a number of thoughts, and I think that Fred's comments really queued up some of the things that I'm going to say very nicely. What's on the screen is an example of what we're talking about. This is a 2-passenger, battery electric, fully autonomous proof of concept airplane that at Aurora we called Pegasus, and Boeing said we have a Pegasus, so it's called the personal air vehicle. But this is a vehicle that is in flight testing now, began flying about a year ago, and which I will use as sort of an example in some of my comments. I wanted to kind of speak to three things very briefly here today. One is to talk about some of both the promises and the challenges of electric propulsion. We talk about we sort of take electric for granted, like we do now in cars. There's some important differences as you start to talk about using electric for aircraft. I want to briefly speak to those. I want to be even briefer on the importance of autonomy, which could be a whole talk in itself, but which I think is really fundamental, not to making these things technically work, but to making them economically viable. And then the third is to sort of talk about the applicability of rapid prototyping, because as it's been said, that the most important thing you learn when you work with hardware is humility. And it's only by really building this stuff and trying to put it out into the field that you really learn what's going on in there. I think when we start to talk about electric propulsion, which underpins many of these concepts, it's worth looking back and going, well, there was a time when people thought gas turbines wouldn't work either, right? And this is a statement from the National Academy of Sciences, a study committee in January of 1941, that basically says, gas turbines, they'll never really work for airplanes. And that's the National Academy is sort of the standard for scientific thought in this. So what I'm about to say on electric should be couched in this, that in the, people were very skeptical of gas turbines, and now, they are the gold standard for airplanes. I want to introduce this concept that there's a hype cycle in any new technology, and this field is no different than pretty much any other. This is not this diagram. I didn't make this. It's It's not unique to UAM. It kind of can be applied to everything, but I think it's worth keeping in mind that not everything you read, and especially not everything you see on the internet, even if it's a video on the internet, you should not believe it because there is a lot of stuff that unless you actually see credible demonstrations first person, I would be highly skeptical of many of the claims that exist in this industry. Remember, the Wright Brothers flew in 1903, but they were very secretive, and it wasn't really until 1908 when they went to France and started flying in public that people really realized what they had accomplished. And, you know, my point is, ask to see this stuff in person. There have been a lot of programs that are going on. The news is full of stuff, and you can decide for yourself where you think we are on this hype cycle. But I would note that, you know, negative press begins. We're not at that stage yet. This is a stage that so far is pretty much getting a free pass from media coverage, and that never lasts forever. And don't get used to that as a way of life. So I would argue we're somewhere still on the left of the peak on that. And that the idea of, you know, for serious long-term proponents of this field is you would like to find a way to sort of smooth through, and if you could, avoid that, the peak and the negative consequences that come with it. I'm not optimistic that we're going to avoid that here in the UAM field. Okay, let me talk a little bit about electric propulsion. Three points on this. Number one, it's not a drop-in technology. Electric airplanes will look different than sort of conventional hydrocarbon-powered airplanes. The fundamental benefit of electric is actually that it adds new dimensions to the design space. If you're a designer, this is a panacea. This is great. The third is that whether it makes sense to do this depends very much on the mission and the performance objective. I think there are sort of three ways electric propulsion kind of buys its way on. One is market potential, which is really about noise and emissions regulations. Sure, you could land an S-76 right out here on the ramp once. I live in a building, my office is right next door to a big operator of helicopters, and you can't hear yourself think when they fly through. The noise is a fundamental constraint on rotorcraft and their diffusion into society. And one of the promises of electric propulsion and some of these new design schemes is that they can get around the noise, and increasingly the emissions is a big deal. So that's one big factor. There are a number of sort of what I would call unconventional missions that they may be useful for, and urban mobility is certainly one of those. High altitude, long endurance sort of pseudo satellites is another potential one. And then allowing you to do things sort of what is called here performance through integration, ideas that may have been around before but really weren't practical without the ability to use the value of distributed electric propulsion. Boundary layer ingestion, for example, is something that people have looked at a lot in the past. The benefits of distributed electric propulsion, powered lift, a lot of the advantages of electric probably fall into those areas. To make this a little clearer, here's a notional commuter. In this case, it's a de Havilland DHC6. It's a twin otter. This is the payload range performance. You can see what it looks like. The heavy line is sort of the nominal performance. The dotted line is what you get when you put reserve. 45-minute reserves. Remember the 45-minute reserves in there. Now, when you put electric in there, the point of this chart is our studies at Aurora, pretty much all the papers at the recent SciTech down in Florida, every study that I have seen says if you just put electric propulsion into a normal airplane, it gets worse. Electric propulsion makes it worse. The factor here, mu, is the factor of electrification. So when mu is 0, if you look at that, all of the energy is coming out of hydrocarbon fuel. You get the performance shown in the black line. If you go to all electric, run it off batteries, you get the green line. Now, these results may vary with the exact case and if you do a clean sheet of paper design, but the fundamental physics drive you to something that looks like this, that the more battery electric that you make this, the worse the payload range performance is going to get. Yes, you see pictures of what is it, a beaver, I guess, that's flying on electric propulsion. What they don't tell you is they just cut the payload range by a very large dramatic factor. Now that may still be okay, but you need to sort of ask the second and third level questions. Just because it's flying, there's a big cost to putting it over into battery electric. So why would anybody do that? Well, you got to look at energy, you got to look at dollars, and you got to look at emissions. The first thing is, so this is now, this plot shows specific energy consumption, so watt hours per pound nautical mile in this case versus range. And again, the heavy black line is the basic, it's the JP8 solution, right? That's what we're used to today. And then as you go more and more electric, you can see how this curve changes. The batteries are very low energy density storage, so they can you can put much less energy on an airplane for a given mass if you're doing it with batteries. However, you can use it much more efficiently. Of the energy that is on the airplane, you can draw significantly more out of it. So for short ranges, there's the potential of being quite efficient in the use of that. Using less energy translates into less money. So it actually could have, these vehicles at short ranges could have conceivably lower direct operating costs. That's a big deal because ultimately all of the things we're talking about will only be fielded if they make money. If they make money for somebody. Technology is interesting, but will never get deployed on any scale if it can't make money. And this curve suggests, yeah, that maybe at short ranges, in this case the crossover point is 200 miles, but again, don't take that number too seriously because it'll change as a function of the designs, but fairly short ranges by aviation standards, there's an argument that you may actually have lower direct operating costs. And with the fuel burn goes the emissions. CO2 emissions basically scale with how much fuel you're burning. Now on an electric airplane, a battery-powered airplane in particular, you're not CO2 free, right? Because that electricity is coming from somewhere. And so these are sort of the standard CO2 emissions from a conventional hydrocarbon airplane engine. And then the electric emissions are coming from the grid where you're generating the power. And that depends on whether you're in the Northeast or the Northwest where there's gas, or in the Northwest, hydro. And here in the Midwest, where there's a lot of coal being burned, it's significantly more. It's still better than the conventional airplane engine, but it's not zero. Is the real point on this? This is another example of sort of the trade space, reinforcing that idea that the efficiency is better. You can turboprops, turbofans, battery, fuel cells in here. And you can see that when you start at 100% in there, and by the time you get to what you're actually delivering useful work to the airstream, you know, turboprops are about 40%, turbofans are down around 33%. That's why the fuel specifics are better on turboprops than turbofans. The battery delivers like 73% in this case, and fuel cells are good, but nowhere near the battery. So the right-hand chart is a log scale of battery energy density versus time. It's a log scale. It's very important because a lot of people say, well, I'll just build a battery-powered airplane and batteries will get better and all my problems are solved. Well, that's not what the historical trend really suggests in there. And the green line at the top, that's JP8. That's a hydrocarbon fuel. So literally 2 or 3 orders of magnitude better energy storage density than the best batteries, and you can sort of see what the battery trend on that is. So yes, it's getting better. No, they're not anywhere close. All electric airliners are not in the future on this, but there may be some possibilities at very short ranges, and that is urban. That's why they're talked about for urban air mobility. In the one of the planes that we were doing at Aurora was something called the VTOL X-plane, the XV-24. It was a DARPA project started in about 2011 to do high-speed transit, but vertical takeoff and landing. And we used a distributed electric propulsion concept that was a hybrid. There were no batteries on this design. We had a gas turbine driving 3 generators, and this was a pretty big airplane because DARPA had specified it that way. It actually had 3 megawatts of power on there. This was probably a program that was ahead of its time. It ran into some real challenges, primarily on the generator side, in developing and proving that. We were doing the airframe, Rolls was doing the engine and the gearbox, and Honeywell was doing the generator. It remains an interesting concept. What really came out of that, though, was the Subscale Demonstrator, which we built here. This was about a 300-pound airplane, which is battery-powered. It demonstrated all of the relevant aerodynamic and control pieces of this design. It's battery-powered vertical takeoff and landing, and fully autonomous in there. In other words, so there's no pilot and joystick. It's all following a script, and you launch it, and it executes the mission, including contingencies, and then lands. So the XV-24 was a program we had been doing when about 3 years ago, Uber launched the Uber Elevate program. And that is really, I think, one of the watersheds in this UAM thing. I think there's a good argument that this conference is happening because of Uber and its declaration that they were going to create autonomous air taxis as a supplement to the ground-based system. That was really driven by a NASA employee, Mark Moore, who left NASA, went to work for Uber, wrote the famous white paper, and is at Uber today. And we Aurora became a partner to Uber 3 years ago, largely on the basis of the XV-24. And this is another example of military technology moving into civil applications. And then, as some of the speakers spoke about earlier this morning, it'll probably move back because one of the early adopters for these vehicles will be the military. But whereas the military was going fast, wanted to go fast, the civil sector wants to be quiet. Both wanted to be fully autonomous for economic reasons. The civil version wants to be simple and reliable. That means as few moving parts as possible, and a big focus on low cost. And so you can see in this picture how the XV-24 morphed into, that's a small subscale of the personal air vehicle, or Pegasus. And this is what the concept of that is. One of the important things to think about in these is, didn't mean to interrupt it there.
Oh, no worries. Just trying to get the sound work.
Sorry. I'll keep going here. Just bring it down a little. Thanks. Is that these are not imagined as personal vehicles. This is not the Jetsons yet. They're done by fleet operators as part of a transportation system. So it's connected into other modes, either driverless cars, rail, whatever, and connecting into probably other existing airline operations. But an operation that is highly automated. In this particular design, takes off vertically with the lift rotors, uses a horizontal propulsion system transition on the wing, and that's what gives it good range. Now, good range is still 30 to 50 miles, okay, so 50 kilometer-ish, but that's the way to get efficient range, is to use a wing, which is, basically a thrust multiplier. So that's the vision that came out of in 2016, and we were actually working with Boston Consulting Group at the time of that. We began working on that. We partnered with Uber. We got bought by Boeing, and then this is what the result was. So this is moving from the cartoon to the reality. And again, this is a fully autonomous, again, battery electric. Same thing you saw in the cartoon. It's just a real vehicle. Just a real vehicle. This made its first flight right about a year ago. And it is currently in a flight test program. There's several vehicles in the program. That's probably about all I can say about it at this point. Other than this is not, there's a long step between this and the bathtub RC model that you saw with some guy sitting in. There are a lot of there's a whole range of people working on this, right? From people trying to use a bathtub to Boeing and Airbus. And this is not a job that's going to be done on the cheap by the time you get everything in there. These are real airplanes, and they cost like real airplanes. I don't know of any other way to put it. I mentioned the range. This is what we think these things will do. So the 2018 50 kilometers is what we think a really good airplane in this category can do. And as the batteries do improve, the range will get better. I put these up there because when you hear people telling you they're going to fly 300 miles on a set of batteries, you should be very, very skeptical, and you should ask them to prove it to you in numbers and in demonstrations, and not just in pronouncements, because physics apply everywhere around the world, and they're very unforgiving, okay? And I go back to don't believe everything you read on the internet, even if there's a video. Especially if a video that no objective third-party observer has witnessed the flight and written it. I talked about electric. I want to briefly touch on autonomy because the debate earlier, will there be pilots? Yeah, there'll probably be a pilot on the first couple, but just think about this. If when you fly in a 747-400, there's like 300 or 400 people in the back and there's 2 people up front. You cannot possibly have a vehicle with economic operations with 2 people sitting up front in a vehicle that carries 2 passengers, okay? We're trying to get the cost down. We're competing against cars and taxis and Ubers, okay? Unless you can get this to where there is a 2 to 4 passenger vehicle with no active pilot on board, there will be controllers, but there'll be network operators like any modern network operation, where they supervise the network and they intervene as needed to particular vehicles or nodes on the network that encounter some unusual situation. The way that we are moving down that track is through something called the optionally piloted airplane, and these are a bunch of different optionally piloted airplanes that Aurora has done. Sikorsky talked about theirs. Aurora was a competitor in a program called ACUS, and another one called Alias, where increasing levels of robotics fly the airplane. Being Virginia, I have to put in our plug on Virginia, where Terry McAuliffe went to great lengths to be able to say he was the first governor to fly on an unmanned airplane when he flew on one of the Aurora Centaurs out of Wallops Island. And controlled the whole thing himself through an app on a tablet. The optionally piloted airplanes are really great for proving out the technology within the framework of the existing FAA regulations. We can fly the most advanced UAVs right out of the Manassas Airport, which is not only in the national airspace and under FAA control, it's actually inside the Washington ADIZ. So, the OPAs are a great interim step for proving this stuff out. I love to show this chart because this encompasses sort of my entire professional career, from being a student to today. And despite all kinds of innovations, the trend, there is a downward trend in the number of licensed pilots in this country in every category except air transport pilots. And ATPs kind of scale with civil aviation, which scales with GDP. But everything else, glass cockpits, digital fly-by-wire, the General Aviation Revitalization Act, which changed liability laws, ballistic recovery parachutes, glass cockpits, the whole new light sport aircraft thing. None of them have been able to break the downward trend in licensed pilots in this country until one thing, and that is the advent of drones. And this is what, when we talk about disruptive technology, this is a disruptive technology at work. And it was mentioned earlier, and people go, oh, well, a drone license, that's not really like a precisely the point. This is a mobile radio telephone, okay? It used to be, to operate one of these, you had to know Morse code and pass a written test from the FCC. And today, every person in this room, I'm willing to bet, has at least one, and some of you have several of these, and these don't even come with user's manuals, okay? It's because the technology is so sophisticated that it takes what used to be a really hard job with a lot of specialized knowledge and turns it into a pleasant user experience so that people can focus on, not on the working the telephony here or flying the airplane in the aviation case, but in using the airplane for something else. Every news crew that I know of carries a drone, right? Every documentary photographer, 70% of the scientists in the polar exploration bases have their own drones today. That is the power of autonomy. It's occurred already in the last decade in the small aviation sector, and it's going to proliferate and propagate into the rest of aviation, which is what's going to make some of these real revolutions possible. But it's already started, and it's going to continue. All right, I wanted to just close with just spending a couple of minutes on the role of prototyping, because as I said, the most important thing you learn from hardware is humility. And just spend a couple of comments on what Aurora was, an organization that I started in 1989 to do UAVs for global climate change research, trying to do very high altitude stratospheric research using UAVs as part of the understanding what's going on with the whole climate issue. We ended up over the last 30 years doing a lot of different aircraft, and then we sold it to Boeing in 2017. This is the summary of the vertical takeoff and landing airplanes, and I put it up there really just to say this is really hard. And again, this kind of goes to my thesis that I love home inventors. I think America is built on small companies, but this is a really hard problem of getting these things out and certified into the national airspace. It's not just a hard technical problem. There are many, or airplane or propulsion problem. It's a very hard controls, a very hard integration, and a very hard certification challenge. And so we did a whole series of things, starting with the DARPA micro air vehicle program. The military's been involved in this in the 90s, trying to develop really small UAVs. We did a whole series of ducted fans. Then we began to go to multi-rotors. Then we experimented with all kinds of propulsion, from gas to heavy fuels to turbine electric, batteries, and so the technical underpinnings of what's happening in UAM don't just spring out overnight. They build on a whole history of government programs and private sector programs that produce the kinds of things that we're seeing today. Doing that with a fairly small group of people. At Aurora, before we were Boeing, we never had more than about 500 people in there. It was partly because we focused on just doing rapid prototyping. We had the capabilities all within one organization, and we made sure that the programs drove the organization and that the functional groups provided support. There was a lot of reuse. It was a culture that was very focused on innovation and rapid results. We used a spiral development process, and we hired people from around the world. Bringing in new talent from around the world is a super important thing that's very easy to lose sight of, particularly in this country today. Very strong focus on customers, and it was highly competitive. One of the things I love about small businesses is they're never very far from extinction, and so it really does focus your attention when your challenge is to meet next week's payroll, or where you're focusing on how many payrolls down the road do I have visibility to. And then we did it a lot. I mean, it's like anything else. You want to be practical. This is, one of my engineers gave me this a while back, and it really is, I use this in all our program management classes. I think it's very appropriate. It'll be very familiar to many of the people in this room. But, you know, you start out thinking, this is the best idea ever, and then you kind of go down, this is fun, oh, it's harder than I thought, it's really a lot of work. And then it's this dark swamp of despair that you get into, and many programs die there, right? This is the inverse of that hype curve, right? The hype curve goes up, and then reality sets in. Well, this is where you start the project going, this is going to be awesome, and then many programs never make it through there. That idea that there's a bridge, that there's something that gets you through, is really true, right? And often it's things outside the immediate part of the organization. It's persistence and belief. It's the importance of support structures, your family, a balanced community, a sense of humor, and eventually you get through there. And I always said our goal at Aurora, my goal as the CEO, was to make this last statement, that this is one of the things I'm most proud of, be something that everybody who worked there felt, and hopefully many, many times. We had two really big patron saints in this. One was Kelly Johnson, one was Clay Christensen. I think if you want a short management course on how to do this, most of what you need to know comes from those two guys. It's really remarkable. Kelly talks about the management of programs, and Christensen talks about why small companies, why disruptive innovation generally comes from small companies and then gets picked up by big companies, and all of his points, I think, have been proven out in the UAV revolution. A lot of removing barriers to success. In the interest of time, I'm going to skip through that and just kind of leave you with this, where this is today is the real challenge is certifying autonomous flight. That is, to me, the really big rock in this. Boeing is putting a whole new, it's called the Boeing Aerospace Autonomy Center in Cambridge, Massachusetts, that is built on the Aurora operation there, focused towards how you develop highly reliable autonomy. I'll just digress slightly. The landing on the Hudson came up earlier. You know, in the UAV world, well, to take nothing away from Sullenberger, had that been a UAV, the route could have automatically been replotted, and you could have landed. They had the energy to land back on the runway at LaGuardia in that, and so I am firmly in the camp that properly done autonomy will make flight safer than it is today. That's one example. The detect and avoid is going to be the big example, because most people don't realize what terrible detect and avoid devices the human eyeball is sitting in high-speed airplanes. Anyway, autonomy is the frontier, and then sort of get off the stage. Number one, UAM is progressing through the high-tech hype cycle. Caveat emptor. So don't believe everything you see. What am I worried about? I'm worried about early passenger carrying accidents from people who put airplanes out there that are not developed and certified to the standards that all of us are used to on Part 121, certified commercial airplanes. I also worry about the Theranos effect, where people make grandiose promises that cannot be achieved, that border on, deception, which, by the way, is against the law in the United States. If you knowingly advertise stuff that is not true in the interest of raising money, I think those are two big threats to our community. Point number 2, battery electric VTOL will have very limited range, okay? I'll say 50 kilometers, maybe 50 miles, but it's going to be short compared to everything else. Maybe that works, but most airplanes I've been used to, people always want more payload and more range, or both. And the battery electric will be very limited in that growth capability. Point 3 is autonomy is essential for cost-effective operations at scale. Sure, you can make these things fly, but we already need 850,000 new pilots in the next 25 years just to fly the big commercial stuff that's already on order. And when you start to talk about the kinds of things in UAM, the numbers just don't work in at least the numbers we've been trying to do. And the only way to really learn on this stuff is to try it out and do it. And that's I think that's one of the things that makes this whole field so exciting, is that there is a lot of experimentation going on. For the students in the room, people at the early stages of their career, this is just an amazingly rich area to be working in, and I highly recommend it. Personally, my bet is on hybrid electric and on regional scale. I think that batteries are going to prove to be too constraining. I think the VTOL is very expensive from an energy point of view, and that translates into a gross weight point of view. And ultimately, the winners in this game are going to be the ones who can do it safely at scale and make money doing it, okay? So the economics are super important, and that's really the focus of what my new efforts are being directed in that. So with that, George, thank you. I know I ran over a little bit into that, but I hope these are in some way useful to the theme of the conference. So thank you.